So we're going to take a look at Chapter 8, which is going to be a t-test, which is where we're going to start inferential statistics, where we're trying to make decisions based on a data set. So the first question is, what is a t-test? There are several different types of tests in statistics. So a t-test specifically is going to compare two means to see if they are significantly different from each other. So significantly different is a very important phrase because they can be different but not have enough variance in them to be significant. So any test that uses the t-test family of distributions is a test of what we call the correlation coefficients. The regression coefficients are also called t-tests. We kind of have a grouping of things that fall under this concept. A t-distribution is similar to the normal distribution. It looks very similar, but the exact characteristics of the distributions can vary slightly based on sample size. So we can't really hold to the whole idea that the one standard deviation is 34% on either side. So there are some differences that can occur within a t-distribution. But overall, they are bell-shaped, they're symmetrical, they have the mean, median, and mode in the same place. So the shape of a t-distribution depends on what we call the degrees of freedom. So the degrees of freedom, if I'm doing a one sample t-test, would be n minus 1. So if I have 100 data points, the degrees of freedom would be 100 minus 1, which is 99. For independent samples t-test, which is less common, we would do n plus n minus 2 because I'm looking at multiple samples. So if it was 100, it would be 200 minus 2, which is 198. So that calculation is really important because that's going to play into using the chart. As the degrees of freedom get smaller, the peak of the distribution gets lower and flatter. So I'm moving away to a lower curve the fewer degrees of freedom that I have. The tails get a bit higher above the x-axis, which gives us a higher frequency of extreme values or outliers, and fewer values near the mean. As the degrees increase, then it gets more like a normal distribution. So a lot of times we use a t-test with a very small sample size, and then as that sample size gets larger, we start seeing it approach the normal bell curve. With a degree of freedom of about 120, we can pretty much say that it is very close to being the normal distribution. So if we are using a t-test, we do try to have a larger sample. In a one sample t-test, the whole purpose is to determine if there's a difference between the mean of the sample mean and the population mean is significantly different. So an example of this would be, does my random sample of 100 high school seniors differ from the whole population of high school seniors with the average on their standardized math test? So maybe you gave 100 seniors some extra prep help, and so you'll look at their mean, you'll compare it to the population's mean on the test, and that'll help you say, wow, this intervention really worked, or wow, it really wasn't significant, so it didn't work. So that's why we compare the means. We have one independent variable that's measured on an interval scale, and we're going to compare that between the sample and the population. How this works is the standard error of the mean is calculated using the sample size and the standard deviation, and that's going to be the denominator for the t-value. That's why we learned that last week. And it's used to divide the difference between the sample mean and the population mean. And the result is what we observe as a t-value. And we're going to use Appendix B to be able to work with those t-values. And Excel is going to do a fair amount of this number crunching, so don't panic over some of the formulas you're going to see. We use the independent samples t-test when we want to compare the two independent samples on a given variable. So independent means the members of one sample do not include or are not matched up with members of another sample. An example would be comparing the average height of 50 randomly selected men to 50 randomly selected women. So we're not trying to keep homogeneous characteristics between our groups. When do we conduct an independent samples t-test? So we need one categorical variable or nominal independent variable. They have to be those two things with two categories. So we need that, and then we need one continuous interval scale dependent variable. And so in this type of t-test, we want to know whether the average scores on the dependent variable differ according to which group it belongs to. So the conceptual issues that happen here is we start asking ourselves, is the difference between the sample means larger than what we expect? Is the difference more than we expect? And in other words, the difference between the sample means has to be large relative to the size of the standard error. So we have to think about what is large in the context of our sample size, in the context of the standard error that we expect to see. So we're not just interested in, do these two samples differ? Are these two means differ? We're also interested if the differences are large enough to suggest that there could be a difference in the population. So context, incredibly important. Just because they're two different values doesn't mean they're actually significant. Here are some conceptual issues with the independent samples t-test. We want to know what our observed difference is between the two sample means, and we want to know the standard error. So we have this general formula. So one of the conceptual issues is that there's quite a lot of calculations that have to happen here. So to find your t-value, you've got to go through the standard error process that we already learned about, and then you have to take the difference of your sample means. So it is a bit of a conceptual blocker there that you have to do all those calculations. The standard error or the difference would be what we're using here, which is the average expected difference between two sample means. So based on my sample size, what is basically acceptable for it to be different? We know two things are never going to be identical in calculations. And then we have to determine the significance of the t-value within the sample t-test. So we have to take into account how many degrees of freedom do we have. We know as we get to 120, we get to that close to that normal curve. And as we fluctuate between that 0 and 120, the shape of the distribution does change significantly. And so when we're finding the probability, using Appendix B, of getting that t-value by chance, if the observed t-value exceeds the critical t-value, then the result is statistically significant. So the observed one is the one we calculate, the critical one is the one we need to meet. If it's exceeded or greater than, then it's not significant, which means the researcher will reject the null hypothesis. If the opposite is true, we will fail to reject the null hypothesis. So with this test, we're looking at a critical value for the t-value and our actual observed calculated t-value. So let's suppose I want to know whether men and women differ in their enjoyment of a TV show. Logically, we probably know the answer is yes. Let's say that I collect a random sample of 50 men and 50 women to measure their enjoyment of the show. Then I do a t-test, and my calculated t-value is 2.5. With an alpha level of 0.05, this would be statistically significant because the alpha level at 0.05, if I look at the graph, let me see if I can enlarge this graph a little bit here. The critical t-value at 0.02 would be 2.39, which 2.5 does exceed. At 0.1, it would be 2.66. So I'm basically going to be using that appendix to find what is the critical value for an alpha level of 0.05, and I should see that that is statistically significant. The effect size is another calculation that we're doing within a t-test. So this is kind of a separate idea from the actual t-value. An effect size is going to measure the impact of something. So to do this, we use what we call Cohen's d. And this determines whether there's a practical significance or a significant impact happening that warrants further research. So we would calculate a confidence interval, like we did earlier, for the difference between the range of the sample means. So we're going to apply that confidence interval calculation. The effect size formula is here. We are going to be able to use this in Excel in our ALA. And so we're going to have to kind of crunch some numbers here. Once I get the effect size, that's a follow-up to your t-test. So you do the t-test, you get your outcome, and you say, okay, here's the impact that I calculated that this result has. So the impact of what's going on. So it could be that they are statistically significant, but maybe there's not a huge impact on the population, and that's normal. So that's why we have to do that follow-up calculation. The dependent samples t-test can be a little bit less challenging for some learners. It's used to compare the means of a single sample or two matched or paired samples. So an example of this would be students that took a math test in March, and then the same group took the same test 2 months later, so like a pre-test and a post-test. We could compare their average scores on the two test dates to have a dependent samples t-test. So basically the key here is that we're not changing anything. Same people, same assessment, same way that we're calculating the mean. And in this, much like the independent one, we're still really just interested in, is the difference that we're observing truly important and valid? Is it truly significant? Instead of comparing two samples and a single dependent variable, we are comparing the average scores of a single sample across two variables, or the average scores of two matched samples, meaning the same people. So the equation for the dependent variables t-test, again, we're going to crunch these numbers in our software, but this is how we would calculate them. The standard error, very similar calculation, but slightly different formula. So this is how we would calculate the standard error for this situation. And then we have the statistical significance. So once the observed t-value has been calculated, we use the same procedures as the independent test to determine it. So it's all going to be the same, still using the appendix, still using the alpha level, except the degrees of freedom, because the number of paired scores minus 1. So if I have the 50 and the 50 taking the test, then that's going to be the 50 and the 50 and the minus 2, like we saw earlier in the formula, because I have to take away 1 from each group. So here's, whoops, went back instead of forward. Here's an example of a dependent t-test. So I want to know what's going on with the sample of student achievement. I'm going to measure it using GPA, and I'm going to look at the GPA changing from 5th grade to 6th grade. So I'm going to collect their data, and I'm going to compare the average GPA of the 5th grade to their average GPA in the 6th grade. Notice my people aren't changing, but their grade is changing. I can calculate the observed t-value, so using all my data, as 8.19, and then I need to know, is that statistically significant? So here is my t-value for my alpha. Here's where I'm at. I am in the region of rejection, which means I'm going to reject that because my t-value is greater. So here's a quick slide with the comparison of independent samples. In an independent sample, I typically have a treatment and a control group, whereas the dependent samples, I have a before treatment and after treatment group, and it's the same people. And then here's the summary, and the summary gives us a kind of a quick look at what we talked through. Again, don't stress out over the calculations. We're going to be using the software to crunch those numbers. The main focus is going to be, when do you reject that things are significant? When do you fail to reject it? And then the significance of being able to interpret what's happening in that t-test.